Hi and welcome to this week's lecture. This is Dr. Daniel Kadlec from the Edith Cowan University in Perth, Australia. Today we're going to look at change direction and agility performance. We'll discuss what change of direction and agility is and how our understanding evolved over time. Then we'll be looking into why certain change of directions are so closely linked with knee injuries and what we can do from a training perspective to prepare athletes for such in-game demands. So another rather complex topic. And this is the area of research that we are involved at the moment.
In the first part of this lecture, we'll look at the challenges in defining change of direction and agility performance and the subsequent coaching implication with a focus on quote-unquote worst-case scenarios during sidestepping, as this is an area that covers, on the one hand, your performance determinants, as in how to sidestep someone, and on the other hand, injury risk, particularly around your knee joint and your ACL. And since both aspects are inherently linked to the availability of time prior to and during the sidestepping task, this will show us the range of possibilities we as strength conditioning coaches have to impact this essential task with our training and prepare our athletes for such demands and make them as robust and resilient as possible. So let's start with the most formal introduction into this topic, and let's first check out how agility is defined so we understand what we are actually dealing with before we start thinking about possible interventions. So Young and colleagues came up with the first definition with this typical differentiation into the perceptual cognitive aspect with its simple components and the more mechanical change of direction speed attributes. Then Jeremy Shepard added anthropometrics and left and right differences to the right side. In 2011, Ian Jeffries tackled the whole agility approach from an ecological dynamics perspective and further differentiated the perceptual cognitive abilities into perceptual constraints and highlighted the importance of gaze, focus, attention, quiet eye, while adding concentration and problem solving to the cognitive constraints part. And on the right side, he not only added the fiber type subcomponent, but also divided the term change of direction speed into motor control and physical constraints, and also added motor pattern development, selection, and adjustments, which basically just rewords what the technique looks like. Finally, Young and colleagues highlighted in 2015 the importance of your core and trunk control. Then, finally, it was highlighted that contraction modes need to be mentioned as well. So here we are now. We reached the pinnacle of confusion in 2023. While all those components are 100% justifiable, with at least one study showing us its significance on selected change of direction or agility tests, I doubt that even with unlimited resources, we will ever be able to find what the limiting factor in your athlete is, especially when it comes down to everything perception or cognition. Also, I'm very confident that in the future, this definition will just keep on evolving and growing with more and more perfectly reasonable yet utterly reductionistic assumptions. So what are we doing? And because I had a hard time getting any coaching implications or a sound understanding out of such broad definitions, we proposed a slightly different way how to define and visualize your multi-directional movement skills, aka your ankle breakability. And while change of direction speed and agility are concepts that have been explained and researched before, we added maneuverability into the equation. And the purpose of maneuverability is to maintain velocity, removing clearly defined the planned step, or to describe a change of direction when one changes modes of travel. So think about going from a shuffling motion into backpedaling and then running straight in a line again. So just this maneuverability of changing the modes of travel. So compared to the previous slide with alleged causal relationships of single attributes and their impact on the overall performance, we want to emphasize that everything is rather intertwined and connected, and deficits in one area can be masked by other attributes and abilities, which make it even harder for us coaches to pinpoint what to do and what to coach. And this is rather a fair description of what's going on in reality, in my opinion. So what now? Given we have close to an unlimited number of change direction and agility movements, which ones do we want to test, train, and ideally improve? How do we determine what's of importance, especially considering that even two cutting tasks? And here in this table, you see key kinetic and kinematic features of a 45 and a 19-degree cut. And both of them are more dissimilar when we look at the significance levels of those key kinetic and kinematic features. So because they are so different, we would need a separate approach for either of them. But we not only see differences between tasks, even within the same change of direction movement, participants do also show meaningful side-to-side differences, which is not surprising. What we see here is in panel A, the vertical ground reaction force of a 45-degree cut on the preferred and non-preferred side. No real differences here. Panel B is the knee valgus moment during ground contact. Here we start seeing a qualitative difference in the timing and the magnitude of knee valgus moments. And in the bottom panel, we have the knee valgus moments plotted for each participant and for each trial for the preferred and non-preferred side. And we see some participants have up to almost 50% left and right differences in the magnitude of peak knee valgus moment. And this can get tricky when we're thinking about agility drills. So unanticipated reactions. How do we equalize the volume here when running such drills in order to potentially improve one side over the other? So if we take a team sport as an example, there's an unpredictable amount of multi-directional movement patterns occurring, and we just can't train them all. So let's rather focus on some key movements that we know can impose a threat to the athlete in terms of injury risk. And a common injury pattern that we see are non-contact ACL injuries during sidesteps and the linear deceleration part prior to the intended sidestep. This is our worst case scenario in terms of multi-directional movements. So if there is even a small chance of something going wrong, it inevitably will sooner or later. Murphy's Law. And our best chance is to prepare our athletes for such worst case scenarios. The fact that we injure ourselves is just fascinating and intriguing at the same time when talking about non-contact ACL injuries. How is it possible that our body goes harder than it can tolerate? Or in other words, we are doing something, although we at least subconsciously should know we can't handle. Yet it happens all the time, as we see here in this video, across all sports, NRL, AFL, NBA, soccer, netball, whatever. And now the funny thing is, it not only happens in sports or in broader terms movement, but also in a cognitive setting, such as learning for a test or planning a project. And evidence from social sciences tells us that we consciously and subconsciously overestimate our own abilities and display more often than not an overconfidence while simultaneously underestimating the demands of the task in front of us, inevitably leading to, catastrophic results. So there seems to be a mismatch between the perception and reality. Let's have a look now at what's going on in terms of biomechanical risk factors to increase our understanding what we can impact with our work. Again, knowing that an injury is a consequence of the load applied is exceeding the tissue tolerance, we have to somehow modify the way those external loads are applied and perceived. And with external load, we know that high knee joint moments in all planes can strain the ACL up to a point of tissue failure. And commonly, knee valgus moments are considered to be dangerous and sinister, but more on that later. So we can now strive to change or decrease the amount of external load applied by changing an athlete's technique or kinematic strategy. There has been done a lot of research looking at this, but to just highlight some key aspects, we've seen that trunk and pelvis kinematics are associated with knee joint loading, especially when highlighting the enormous mass distribution between your huge upper body in relation to the rather tiny legs. Any changes to trunk dynamics will affect distal limb joint loading. Further, when looking at ACL injuries, we often see an extended knee posture at ground contact. And with every degree of increased knee flexion, we are decreasing knee joint loading. And most recently, we've seen that foot mechanics, i.e. heel or forefoot contact, and where the foot is pointed to while sidestepping, affects, again, your knee joint loading. So this is talking about the kinematic strategy, your movement technique. But when the applied loads are high, we need to make sure that those loads are within what our muscular system can tolerate. And this is probably nothing new, but muscular strength around your hip, thigh, and your calf complex contracting at the right time can stabilize the joint and mitigate joint loading. And such an overview makes it look fairly easy what to do. Just manipulate any of those aspects in isolation and you'll be fine. Yet, unfortunately, it's not that easy, especially when it comes to deliberately changing movement. Clearly, the mechanism of this injury is multifactorial, but what explicitly do we know that elevates ACL strain? What in vivo and cadaveric research has shown is that it is the combination of tibiofemoral compression, anterior tibial translation, and valgus and/or internal rotation knee moments that elevate ACL strain, and importantly, it is the combined loading of these moments and forces that contribute to ACL strain and likely injury risk. And some of the technique or kinematic aspects that do elevate ACL strain are shown in the right hand figure. So have a look. And now some further considerations. How is your available range of motion affecting ACL strain? Let's say your athlete has inherent mobility limitations in their hips due to FAI, femoral acetabular impingement, and it needs to compensate for this through other joints. And the next joint in line in the kinetic chain is the knee. And the same thing if you go from the ground up. Limitations in your ankle can affect knee biomechanics. And we touched on trunk and pelvis kinematics already, but again highlighting that an ACL injury is more than just your lower limb alignment. And from a muscle point of view, elevated quad and breaststroke forces during the initial contact of your sidestep or of your foot during sidestepping may represent a generalized muscle strategy to increase knee joint stiffness, protecting the knee and ACL from external loading and injury risk. So it's not just your glute medius that we want or should be considering of being not strong enough. So side steps are a high risk but also high reward movement. Either way, someone can get bruised badly. We know this movement tracks the highest amount of non-contact ACL injuries. So again, by definition, you're hurting yourself. You're expressing higher forces than your tissues can handle and sustain. And this happens so incredibly quick that we just have zero chances to correct anything once your foot hits the ground. In less than 50 milliseconds after your foot hits the ground, your ACL is done. To visualize how quickly your ACL goes, this video of a sidestep is at 1/10 of real time, and the red lines indicate initial contact and weight acceptance, which is the time frame your ACL typically goes. And this is in real speed. And this is just how much time you have available once your foot hits the ground. Pretty quick. So good luck trying to cue your athletes on what to do, or rather not to do, during the execution step in terms of movement kinetics and kinematics. So your movement technique. And despite the literature repeatedly showing us that ACL injuries are a multifactorial and multiplanar injury, we tend to dilute it to only the frontal plane and knee valgus. And therefore, most of the recommendations and mini band interventions are trying to minimize knee valgus angle. However, what I'd like to bring up is the question, is the knee valgus angle the cause or merely the consequence of ACL injuries and the last occurrence in the cascade of tibiofemoral compression, anterior tibial translation, and then knee valgus / internal rotation? And on the figure here, you see the time sequence of the mean knee angles, so your black line, of 10 cases who suffered an ACL injury with the 95% confidence interval, so your gray cloud around the mean. And time 0 indicates the initial contact of the foot, and the dotted vertical line indicates the time point of 40 milliseconds after the initial contact, so the time period your ACL ruptures. So again, it's not just your knee valgus or adduction angle, but there's a lot happening prior to that as well. And despite the emergence of movement is complex beyond our current understanding, we still make causal inferences between what we see and what's going on, or in other words, between movement kinematics, the how you move, and the underlying kinetics, so forces and moments, the why you move the way you do. Yet again, it's not that easy and simple. What I want to highlight with this paper is our inability to grasp the interdependence of more than just two factors. Here, they measured key kinematic factors, which were previously shown to be a risk factor for ACL strain or elevated ACL strain, and put them in a linear mixed model and a backward stepwise linear regression to see if kinematics predict kinetics. And although we can predict them, there's a reason we need such complex statistical methods to get the answer, because we just can't perceive that. And let's just look at what's going on for the knee valgus moment, which is commonly considered to be a proxy of ACL strain, right? So we have 4 factors which are different weighting affecting knee valgus moments, yet none of them is actually knee valgus angle. So our coaching eye is in no position to perceive that. So you can display no valgus, yet experience huge valgus moments. Or you can display a horrific valgus motion, yet no knee valgus moments whatsoever. And that's the complexity we live in. So bottom line, they do, but I argue in a way the human mind, and especially the coaching eye, cannot comprehend. Another good example is this modeling study showing that frontal plane loading, so your knee valgus alone, is insufficient to strain the ACL to the point of tissue failure. Participants jumped off a box with one leg and did a lateral drop jump, as you can see on the top of the figure with the skeleton, which roughly indicates what happened. So mechanically, a somewhat similar motion to a side step. Then they modeled the ACL force throughout the ground contact phase and decomposed it to each plane. So let me talk to you through this figure. So on the top, you see the total ACL force in a black dotted line, and the right line indicates the ACL force just from the sagittal plane. And then below that is the ACL force coming from the frontal in blue and transverse plane in green. And what I want to highlight here, that the vertical axis is logarithmic scaled. So just the huge difference in the magnitude of ACL force coming through or from different planes. And this is just something to consider for us when we again see someone trying to minimize knee valgus with mini bands. and then trying to get around where the main strain or ACL strain actually is coming from. And similar to our sprinting lecture last week, where we talked about vertical and horizontal forces, decomposing vectors into their components makes the statistical analysis easier, but can lead to misinterpretations and poor coaching recommendations. Similar thing with joint moments. What we usually see in publications are figures like the top right and bottom, where the vertical ground direction force is plotted over time, and in the bottom one you see anterior-posterior forces over time, which are then in the next step separately analyzed. And the left part of the figure shows only the vertical and anterior-posterior forces independent of time. Now, if we combine that as a vector with only two components over time, we get this geometrical sausage, which requires a more sophisticated statistical analysis to get an idea what's going on. And mind you, this is just two components plotted over time. We are still neglecting the third plane, so medial lateral forces, but there is no possibility to plot a four-dimensional figure. Welcome to reality. Okay, zooming out of this, just looking at movement from a biomechanical lens, a major challenge for movement scientists is to recognize that motor behavior they examine in their studies is actually some amalgam of social, cognitive, affective, motor behavior. And because of this complexity and the non-uniform interaction of social, cognitive, affective, and motor features, it is very, very hard to quantify and objectify any changes in movement as a function of different interventions. And research hasn't given us robust information yet on how to do that. And that's why we're surrounded by a dangerously high amount of assumptions and convictions in this industry. Yet we know that convictions are more dangerous enemies of truth than lies.
So, bringing this back to change direction and agility, what are we doing now? Now that we know that kinematics, so that what we see likely does not matter to the extent we are assuming, especially when we're looking at one specific feature at discrete time points, so distinct joint angles or segment dynamics, which ironically is 100% contrary to our obsession with linear cause and effect thinking. Also, this romantic idea about changing technique is again not that simple. In fact, some key questions are still unanswered by research, such as, can we change it? What do we have to do to change it? How long does it take to change it? How long does it stick? And the million-dollar question, does it transfer to other movements? And the most honest answer is, I don't know. And that's why we're facing so much claims and assumptions in this industry. But what I do know is which movements are imposing high loads on the athlete, and we can use this knowledge to reverse engineer the demands and create a progressive exposure to build resiliency and robustness regardless of how the athlete is moving. So we can improve the capacity of the individual movement pattern by knowing how to set up drills and expose them to high loads and push them towards worst case scenarios in a progressive way, which will inevitably happen in a game sooner or later.
Welcome back to the second part of this lecture, where we'll be looking at the training implications on how to prepare athletes for such worst case scenarios that impose high demands on their system and especially on the knee joint. And we want them to get as robust, as resilient as possible with our training. Specific adaptation to imposed demands. So what can I do to elicit high loads in a sidestepping task? Many papers have looked at what contributes to knee joint loading, and the following are the four key aspects we as coaches can use when designing drills to progressively overload the athlete. That is entry velocity, change of direction angle, trunk control, and preparation time. So let's start with entry velocity. Although we see an exponentially increase in knee moments when pushing approach speed, we know that most ACL injuries happen at a moderate speed with about 3 to 4.5 meters per second. And this is a great end goal working towards with our drills, which is probably a slower velocity than most of us might expect right now. And also, we know that ACL injuries happen in the very first moments of the ground contact phase. So, from an injury risk perspective, exit velocity does matter. Yet, we also do want to train for performance. And as we've seen in the video at the beginning, ACLs happen at this odd angle of about 30 to 45, maybe 60 degrees, where the athlete thinks they can, but in reality, they can't. So the steeper your sidestepping angle, the higher the loading up to a certain point. Although during sidesteps or change direction movements of 90 to 180 degrees, high magnitudes of force and torque act on the athlete in all planes and direction, while twisting and turning, no athlete will do that without having decelerated to a sufficient amount before, i.e. just slam the foot into the ground and turn while traveling at high velocities. So this has a rather low priority in my coaching setup, but we still want to prepare them somewhat for linear deceleration movements. Lateral flexion and rotation of the trunk away from the intended direction during the final cutting step increases injury risk. Also, just by shifting the center of mass by 4 centimeters to the intended cutting direction has been shown to have a massive impact on distal lower body joint loading. Failing to align the trunk in a favorable position during the cut or the sidestep will therefore increase joint loading. Disturbing or delaying an adequate trunk alignment during the execution of the change direction or sidestepping maneuver with appropriate task constraints can further prepare athletes for worst case scenarios if progressed properly. So holding a weighted implement in one or both hands or crossing the arms throughout the task are simple methods to sufficiently alter the movement pattern and therefore change joint loading. Here's an example from our research. Same athlete, same condition, same approach velocity, yet, well, no trunk control whatsoever. And the associated knee joint power in the top panel, so the rate of doing work or joint moment times the angular velocity in all planes, is occurring earlier and with a higher magnitude. So if your trunk sway is high and in the opposite direction to your intended cut, then the demands on your knee joint increase. Less time to prepare for a sidestep or change direction task results in greater knee valgus moments. Manipulating the time available to determine the direction an athlete is cutting to is another impactful tool when designing drills. The more time an athlete has to prepare, the less stressful the sidestepping task is, as the athlete experiences lower joint loads. As shown in this paper from Lee and colleagues, where they quantified knee joint valgus moments in response to a pre-planned, so AP arrow planned, to 3D videos of 1 or 2 defenders, so that's your 1D and 2D scenario, or an arrow suddenly appearing, so arrow unplanned. And the only intention I have with those quote-unquote unplanned change of direction drills is to chip away an athlete's preparation time to then increase mechanical loading. And I have zero expectations to improve any perceptual cognitive abilities. And although generic stimuli such as an arrow suddenly appearing or light or you as a coach shouting which direction the athlete has to cut are regarded as highly unspecific to react to, which I fully agree with, they are a very important tool to prepare athletes for similar in-game scenarios when almost no preparation time is available, such as a funny bounce of the ball or someone is trying to tackle you. And here we have two more examples of how to manipulate the side step to elicit a high joint loading, especially around the knee, done in our lab. So let me talk you through this slide. So on the figure, on the graph on the right-hand side, you see knee joint power for 4 different conditions. The red one is the quote-unquote textbook condition. So a side step where we want the foot to be pre-oriented to the right direction with a forefoot strike, knee flexion or with a good amount of knee flexion when hitting the ground, no knee valgus. Hips already pre-oriented to the cutting side, no trunk sway, and yeah, as you see, almost very little joint loading in terms of knee joint power. Then the orange one, pre-planned, just cueing the athlete, go in and cut to your left. You can see a moderate increase in knee joint loading. And then we have 2 experimental conditions, the greenish and the black one. The first one, the black one, let's have a look, is the candy condition. I cued them to sell the candy. So yeah, throw your trunk in the opposite direction to deviate your athlete or your opponent, so to say. And yeah, that increased and spiked knee joint loading. So something we can also use as a task constraint to further elicit higher joint loadings. And the last one, the greenish one that we labeled punch, the athlete is holding a 2.5K plate, and then in the moment, or ideally in the moment of your foot hitting the ground, you accelerate the plate away from the intended cutting direction, and therefore you accelerate the center of mass to, again, the opposite direction. And as we see, this further increases knee joint loading. So again, just bearing in mind how we set up our drills and how we want the movement execution to look like if we want to increase robustness and resiliency. So again, is it worth to quote unquote train with a perfect technique all the time, or do we want to challenge our athlete to become more robust and resilient in the long run? And now in this short video, you'll see some sidestepping drills with various progression and how it can look like to prepare athletes for such game demands. So first we increase the approach run and therefore approach velocity. Then we increase the change direction angle. We now add a trunk constraint by just crossing the arms and holding a footy, and then add an unspecific time constraint. So the athlete has to react in the last moment. And this is just a variation of how to combine all of them. Additionally to the sidestepping drill that I showed you in the last slide, this change of direction progression is more focused on linear and lateral deceleration. So another part associated with ACL injuries. And I'm applying the same principles in terms of entry velocity, trunk control, and preparation time as with the other drill. So let's have a look. First, just starting with a 3-meter distance and over time increasing the entry velocity by increasing the distance of the 2 cones where the athlete have to run to, then trunk constraint again with a weight, and in the last progression time constraint. So this is a bit hard to decipher, but the athlete behind is yelling the cone color where the athlete has to plant the foot and then cut. Good. And another distinction that I want to highlight with this other drill is that I'm emphasizing now more the inside leg with this drill as compared with the drill before where the athlete is primarily decelerating off the outside leg. So just a variation to equally load inside and outside leg for whatever worst case scenario might happen in a game. So back to the process of free body analysis to get an idea of how to manipulate or rather increase the force vector to achieve a certain performance or rather a change in performance. When we're looking at the position the athletes are going into, we need to consider forces to generate so we can overcome gravity and accelerate or decelerate horizontally or laterally. So what are the limiting factors that cap the ability of humans to run at speed and change directions? Well, a big part of it is our leg extension force capabilities. As more force is oriented horizontally or laterally during cuts and change direction, or any task that require a change in the path that we're traveling in, less vertical force is available to overcome gravity quickly. Hence, we typically see increased ground contact times and also reduced travel velocities because we still need a sufficient vertical impulse to not crumble. So it's a trade-off between staying on your feet and changing the path of travel while in motion. But there's more variation in the ability to turn, sidestep, and change direction with high velocities than can be explained by their leg extension force capabilities alone. And this has been shown repeatedly that a much lower correlation between your leg extension capacities and your change direction, and an even lower correlation between sprinting, straight line sprinting, and agility exists. So this tells us that there's more going on. While leg extension force is important, there seems to be other very meaningful aspects that determine how well an athlete moves in a multidirectional way. But let's remember, human movement is still governed by Newton's laws of motion. And this aforementioned law of correlation reflects an athlete's ability to utilize their leg extension capacity within the specific skill, within the multidirectional task. However, this leg extension capacity is typically tested with sagittal-based lift, so your squat, 1RM, IMTP, or leg press, or any other variation of that. And now, during multi-directional movements, we are now potentially required to control forces and moments in the frontal and transversal plane. And despite athletes having high leg extension capacities in the sagittal plane, they may not be able to turn or utilize that effectively in other planes. That's why you typically see studies showing a low correlation between such tests and the change direction performance, and unfortunately conclude that strength isn't important, which isn't the case. We need to be able to control forces in other planes to effectively utilize your total leg extension capacity. And this takes time, and we usually don't see that in our 4 or 8 to 12-week strength training intervention studies. So despite increases in your squat, leg press, or clean 1RM, let's say. And again, unfortunately, they typically conclude that strength increases don't matter, which is not the case. And we need to be very careful when we read and interpret such literature. So how can we support our multi-directional performance with our work in the gym? How can we best increase our leg extension force expression capacities? And what can we do beyond the generic approach of just getting stronger? Can we maybe focus on single contraction forms to elicit a greater transfer to on-field performance? And here is some in-house research that assess the contribution of your isometric, eccentric, concentric, and dynamic strength in different change direction and agility tests, and did this for faster and slower athletes based on the final time to see if there is anything worthwhile going on with some strong practical implications. But first of all, both change direction tests were significantly correlated to maximal dynamic, isometric, concentric, and eccentric strength with a very large correlation. But if everything is important, nothing is important. We need to be holistically strong. And even when looking at the percentual contribution to the performance of different change direction and agility tests, we see hardly a difference between faster at the top and bottom in the lower figure between fast and slower athletes. So is being strong important? 100%, no doubt. But beyond that, contraction form specific strength, the published literature is very thin. We've already spoken heaps about the importance of trunk control for side steps. especially the ability to control your trunk as it affects your knee joint kinetics down the chain. Here, to visualize it again, we see the difference in lateral flexion between planned and unplanned side steps. But control comes from strength. Can't control something if you don't have the physical capacity to do so. And this requires a sufficient overload that most Pallof presses probably won't elicit. Just some food for thought. Similarly, we don't want our athletes to be restricted in any joint, as this can affect energy flow and put us in positions we don't want to be in. But again, your bended ankle, knee to wall, and your 90-90 hip stretches are probably insufficient to do so. So how do we train the physical capacities that matter for multidirectional movements in the gym? Or what can we focus on other than actually executing the change direction or agility movement? Pause this slide here, have a read, and think about the exercise selections that come with the listed training methods. Similarly, we can incorporate task variations and progressions during the execution of sidestep or any change direction movement of importance to focus on certain areas we want to stress and overload. The goal is to be able to change direction despite the position you find yourself in, not only when you get to choose the position you're in. So we want to prepare the athletes for the demands they will inevitably face in competition. And this likely won't come from executing quote unquote perfect reps over and over again. We need to challenge them. So let's recap this lecture. Again, physics govern movement and change direction performance. So what components affect agility performance? What are the definition and what is important that affects your total agility performance? How is time linked to ACL strain, and why does it matter with our strength conditioning practice when we set up drills and exercise selections? What mechanisms are straining the ACL? So what is the occurrence when an ACL goes, so we know what to work towards in order to reduce the likelihood of it happening. And how do we increase the demands during side steps especially when thinking about what our worst case scenario is.